For years, scientists have convinced us that the universe is constantly expanding. This belief has fascinated scientists and academics who have adopted the Big Bang theory as the most widely accepted explanation for the origin and evolution of the universe. According to this theory, the universe began in an extremely dense and hot state, and has since undergone continuous expansion. However, the James Webb Space Telescope has made a surprising discovery that challenges this theory. How did the Space Telescope challenge the idea of expansion, and what does this mean for our understanding of space? Join us as we take a look at the recent shocking find from the legendary James Webb Telescope. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel. Be sure to like this video and turn on the notification bell. Albert Einstein's general theory of relativity provides a framework for understanding how the presence of heavy objects bends space-time. According to this theory, the cosmos originated as a singularity, a point of infinite density and temperatures approximately 13.8 billion years ago. According to the Big Bang theory, all matter and energy were found compressed into an extremely small, hot region. At this point, the cosmos began to expand with a rapid and violent event known as a Big Bang. During the first few seconds following the Big Bang, the singularity experienced a massive release of energy. The universe was filled with an extremely hot, dense, and energetic plasma containing protons, neutrons, electrons, and their antiparticles. As the universe cooled due to its expansion, the temperature dropped enough to allow the electrons to bond with protons and form neutral atoms. This process, known as recombination, allowed protons to move freely through space, resulting in the cosmic microwave background radiation that we can detect today. The stretching of space-time itself may represent the expansion of the universe. This stretching does not imply a movement through a space where objects move away from central point, but an expansion of space itself. We can imagine as the surface of an inflating balloon. The points on the surface move away from each other as the balloon grows, not because the points are moving, but because the space between them is expanding. Similarly, in the case of the universe, galaxies and other celestial objects are pulled by the expansion of space rather than away from it. So, what is the source of this expansion of space-time according to scientists? Dark energy is a hypothetical form of energy that is thought to permeate all of space and exert a negative pressure. This dark energy is thought to be the case for the accelerating expansion of the universe. In recent decades, observations have revealed a phenomenon crucial to understanding the importance of dark energy: the balance between gravitational forces and the expansion of the universe. Gravity, an attractive force acting on massive objects, tries to slow down the growth of the universe. If the universe were composed solely of matter, such as galaxies and their corresponding mass, gravity would eventually stop the expansion and give rise to a phenomenon known as the Big Crunch. However, observations reveal that the expansion of the cosmos is accelerating rather than slowing down. This implies the existence of a repulsive force that counteracts the effects of gravity. This repulsive force is generated by dark energy, which is uniformly distributed in space and exerts a negative pressure. This precise nature of the energy remains one of the greatest mysteries in modern cosmology, and scientists are actively investigating its characteristics. Although dark energy is responsible for the accelerating expansion, the distribution of matter in the universe also plays a crucial role. The density of matter and energy influences the curvature of space-time through the equations of general relativity. Regions with higher density exert a stronger gravitational pull, which slow down the expansion of the cosmos. On the other hand, regions with lower density experience a weaker gravitational attraction and contribute to the overall expansion of the universe. Matter in the universe is not uniformly distributed, but is organized into massive cosmic formations such as galaxies, clusters, and superclusters, which are interconnected by vast cosmic red-shaped filaments. These structures form due to the gravitational collapse of the regions with higher density under the influence of gravity. As the universe expands, these cosmic formations experience a stretching of space-time. However, gravitational forces within these structures counteract the expansion to some extent, resulting in a complex interaction between the expansion of space-time and the gravitational pull of mass. On larger scales, the expansion takes precedence, resulting in a continuous stretching of the cosmic web. It is important to note that the expansion of the universe does not imply that galaxies are moving away in space. In fact, galaxies may move closer together on smaller scales due to the influence of gravity. However, on a larger scale, the overall effect of the expansion is to increase the distances between galaxies over time. Various observations and abundant evidence for the expansion of the universe. One important example is the redshift of light emitted by distant galaxies. As the universe expands, the wavelengths of light from these galaxies are stretched, shifting towards the red end of the electromagnetic spectrum. This phenomenon, known as the cosmological redshift, provides compelling evidence for the expansion of space-time. Another important piece of evidence is the cosmic microwave background radiation, or CMB, which is a remnant of the hot early universe. The CMB shows a surprisingly uniform distribution of energy across the sky, with small oscillations that reveal important information about the initial conditions and subsequent evolution of the universe. Extensive CMB investigations have confirmed predictions of an expanding universe and strengthened the Big Bang theory. Observational data from large-scale surveys such as the Sloan Digital Sounding and the European Space Agency's Planck satellite project have provided accurate information in recent years about the expansion rates of the universe and the distribution of matter and energy within it. These discoveries have improved our understanding and contributed to the ongoing research for information about the underlying nature of the universe. One of the most fascinating aspects of the James Webb Space Telescope's galaxy surveys is its ability to map the large-scale structure of the cosmos at high redshifts, when galaxies were still young and grouped into large clusters known as protoclusters. These protoclusters are the predecessors of today's galaxy clusters, which are the largest gravitational structures in the universe. By studying these protoclusters, we can learn about the interactions between galaxies, their interactions with their surroundings, their growth and merger, and how they influence the formation of stars and planets. Protoclusters are extremely rare and difficult to find because of their wide expanse in the sky and low surface luminosity. However, the James Webb Space Telescope's wide-field, high-sensitivity cameras will make it possible to detect hundreds of miles of galaxies in a single observation, covering a significant portion of the sky with unprecedented depth and detail that has never been observed before. Astronomers have the ability to identify protoclusters by analyzing galaxy density, spectral properties, and facial dispersions. To do this, they combine data from the James Webb Space Telescope with other observatory surveys. The James Webb also provides information on the masses, ages, star formation rate, dust content, and gas kinematics of individual galaxies within protoclusters. These observations will reveal the differences between galaxies within protoclusters and those in less dense environments, as well as their evolution over time within their hot structures. In addition, the GW will allow it to investigate the intergalactic median, or IGM, around protoclusters, which is enriched by supernovae and active galactic nuclei, AGN. The IGM regulates galaxy formation by supplying gas for star formation and withdrawing it through winds and outflows. However, images captured by the James Webb Space Telescope are challenging the Big Bang theory, as they show galaxies of enormous sizes that appear not to have been able to exist or are not consistent with the Big Bang theory. These candidates galaxies are estimated to have formed approximately 13 billion years ago, between 500 and 700 million years after the Big Bang. Astronomers have the expectation of observing young, small galaxies in this region of early space. However, images captured by the Space Telescope reveal that the stellar systems may contain about the same number of stars as our own Milky Way galaxy. Instead of finding tiny young galaxies, discovering mature galaxies similar to our own in what was thought to be the dawn of the universe. The James Webb Space Telescope is equipped with infrared sensors capable of detecting light emitted by older stars and galaxies. This allows astronomers to go back in time almost 13.5 billion years to the beginning of the known universe. Prior to the discovery, scientists had detected numerous galaxies in the oldest regions of the universe approximately 350 million years after the Big Bang, using data collected by the JW. These distant stellar systems were small and in agreement with the predictions of current cosmological models. However, the recent discovery of 6 mature massive galaxies in the same region of the early universe raises the possibility of challenging current cosmological theory and modifying what has long been considered and accepted scientific knowledge. It is surprising to think that the early universe could have organized itself so quickly, since these galaxies did not form at that time. These new discoveries emerged from proving a region near the constellation Ursa Major, which was first observed by the Hubble telescope in the 1990s. The candidate galaxies are so striking that they contradict 99% of current cosmological predictions. According to current calculations, there should not be enough material to form large stellar systems 500 to 700 million years after the Big Bang. The researchers believe that to explain the observed mass of these galaxies, it would be necessary to either modify current cosmological models or revise our scientific understanding of how galaxies arose in the early cosmos. Both hypotheses required fundamental change in our understanding of the early formation of galaxies in the universe. These unexpected objects have been humorously dubbed universe breakers and have so far lived up to their name. Although more data are needed to confirm that these candidate galaxies are as large and old as they appear, the data suggests that they are very likely to be real galaxies. There is the possibility that some of these objects are obscured supermassive black holes, which is another interesting aspect to consider. However, the amount of mass discovered implies that the known mass of stars at this stage of the universe is up to 100 times larger than previously thought. Although the sample is halved, it is still a remarkable difference. It is possible that these objects are not galaxies at all. Another possibility is that they are other kinds of strange objects, such as faint quasars, which would be quite interesting. Even if only one of these galaxies turned out to be real, it would have a test of all the hitherto known limits of our cosmological understanding. In the meantime, preliminary observations offer persuasive insight into how the JW could ultimately rewrite our understanding of the universe. The rapid pace of discoveries made by the JW is similar to the early days of the Hubble telescope, which was launched into low Earth orbit in 1990. The Hubble Space Telescope quickly began to provide a much more complex picture of the early universe than researchers had initially anticipated. Scientists have made a new discovery that challenges the idea that the universe is expanding at the same rate in all directions. This finding casts doubt on the widely accepted theory that the expansion rate is uniform in all directions. A recent study, based on the data from the European Space Agency's Newton survey, NASA's Chandra, and the German-led Rosat X-ray observatories, revealed that this cosmological premise may be wrong. A PhD researcher in astronomy and astrophysics at Bonn University, together with his supervisor, set out to investigate the theory of isotropy. According to this theory, the universe has the same properties in all directions on large scales. with small deviations widely accepted as a consequence of established fundamental physics. This premise has been supported by observations of the cosmic microwave background, CMB, which is a direct remnant of the Big Bang and reflects the universe in its early stages, only 380,000 years old. The uniform distribution of the CMB across the sky implies that the universe expanded rapidly and uniformly in all directions in those early times. However, in today's universe, this could not be true. The researchers studied the behavior of more than 800 galaxy clusters in the present-day universe in collaboration with colleagues from the University of Bonn and Harvard University. If the isotropy hypothesis were correct, the clusters should have uniform properties across the sky. However, they observed significant differences. They compared data from X-ray temperature readings of the extremely hot gas found in the clusters with the bright appearance of the clusters on the sky. One would expect clusters with the same temperatures and the same distance to appear equally bright, but this is not what we found. They found that the clusters with similar properties and temperatures appeared less bright than expected in one direction of the sky and brighter than expected in another direction. These differences were quite significant, hovering around 30% variation. Moreover, these variations were not random, but followed a distinctive pattern depending on the direction in which you looked at the sky. What do you think? Let us know in the comments box and remember to like and subscribe, and we'll see you in the next video.